Okay, I think people are coming. So the goal of this workshop is to talk about indexing in general. Hi, Zem, hi, JD, hi, Aziz. Thanks to say hello in the chat. So I'm sure that you are there. The goal is to talk about indexing. Of course, I will run all my demos on Yugabyte. YugabyteDB is Postgres compatible, so most of the thing I'm showing work exactly the same in Postgres. One advantage of running it in Yugabyte, we have added some instrumentation in the execution plans, and I will use that to show you exactly the real cost of the queries before and after adding an index. And you can run the same if you want. In the slides, you will see how to start a Docker container with Yugabyte. You can also run it on Postgres. You can also ask in the chat if you see something that is very different on Postgres than in Yugabyte. And I use a version of Yugabyte that is not released yet. Anyone can build it from the GitHub repo because it's open source, but it's the next version. I use it also because we bring the Postgres compatibility from 11 to Postgres 15 in the next version, and there are some nice things also to see there when looking at execution plans. Okay. So let's start with this workshop, and I'm Frank Pachot. I'm developer advocate here at Yugabyte. My goal is to bring some awareness for those who want to run a SQL application, a Postgres application in a cloud-native platform. So if you don't know already Yugabyte, my goal is to let you know that it exists, which problem it solves, but also help you starting with it. If you do a proof of concept, if you just look at it, if you start it and think that it doesn't have the performance that you expect, the goal also is to help you. A distributed system, we try to make it the most simple and easy to start, but a distributed system is never easy. A SQL database is never easy. So always good to talk in the community about that. That's my main role, also taking feedback and discussing with the product management about what the users encounter. The slides are there. I think you don't really need this because I've put it in the commands. So in the commands, you have the event commands and you have the stage commands. Those are in the stage command, and there are the links to the slides. And if you want to run it on a Yugabyte cluster, here are the two commands that you can run, and maybe I will just do it quickly to show you how it works. So basically, I'm on a host where I have Docker. I will start a container from the Yugabyte image. This is the latest one that is released, and this container will start the cluster. Okay, of course, I did that just before running the workshop to be sure that my command line was okay. So I removed the container to start it again. It just starts. And then to connect to it, we have a shell in the container, but what I like, just because it is Postgres compatible, is to run Postgres simply from there. Let me just run a Postgres image that I don't have here, but it is downloading. And basically, it uses the Postgres image, but just using the client PSQL there to connect to the cluster. And I didn't put a name for my container, so this doesn't work in my environment, but it should work in yours. However, as I mentioned, I will run on another environment where I have a newer newer version 2.25 that is Postgres 15 compatible. So you can run the same where you want. I've started the container, but I do not use it here. I use another one where I have a latest version just to discuss also what will come with the next version. Okay, if everybody is there following, everything is recorded also, so maybe you just want to chill and watch me doing the demo. And if you want to try it at home later, you can. The code is in the slides and in the link that I have put. So maybe you just want to look at me running the commands, explaining what I see and asking questions on the chat about what is there. Let me show the slides. And the first thing I will start, or maybe I will start by creating a table, just in case it takes some time, because I decided to use the latest version, but I've run that on a very small instance where it can take some time. It's just a lab on my laptop. Just setting the pager and showing the version. Dropping the table in case I already have it. I will use an extension just to generate some UIDs. And this is the table that I will use, but I will explain that in the slides. My idea is to start with a very generic table with column 1, column 2, column 3, etc. And we will run a query on it and see what we can index. I'm inserting some rows just generated randomly with generate series, and I will run an analyze when it's done, and then we will be ready to run a query. But first, I will go through the slides there to explain a bit of concepts about that. So the table that I use, you have that in the slide, and the insert that I use there. I insert random values on purpose. I insert them with a different distribution because when we look at indexing, we look at the selectivity of the predicates. So I have different combination there. And then this is the query that I will run. I can use a prepared query just because I don't want to type it each time, and then I will just execute it with some values. Basically, I will read from one table. The first thing is that this is about indexing, and we will look at a single table. When you have joins, then you will also use indexes with the joins, and it's very similar because you index for some predicates and joins have predicates. But first, to understand it, it's much easier to start a lab, which is simple with a single table. And I have a few predicates in my where clause. An equality value, an equality predicate on column 1, a range predicate on column 2 between two values, and in predicate for column 4, which is an equality, but an equality with different values. So you can already guess that we will cover indexing for those different cases because maybe you don't need the same indexes for equality and inequality, but more important, the order of the columns in a single index may be different depending on that, and this is what we will see. You can see that I've also an order by on column 2 and column 3 and a limit there. One message that you should get during this workshop is that you do not index only for the where clause. We will look at the whole query to find the best index, and the where clause are not sufficient. Sometimes you have predicates in the where clause where you don't want an index on it, but sometimes you have also indexes where you will add columns that you do not find in the where clause. Because indexes can improve the performance for other operations. So basically, I will prepare the query, execute it, and execute it with an explain to see the execution plan. I have the output there, but I will just run it now that my table has just 1 million rows inserted and I have analyzed it. I'm running the prepare statement just to be able to reuse multiple time and execute. So I'm executing this statement that I have prepared with value 1 for column 1 and range 24 to 42 for column 2. Okay. And we have a result. I've put the fonts large enough. I think I can reduce them a bit. Please tell me in the chat if it's difficult to read. For the moment, I will just reduce that to show the word line. Sorry. And if it's too small on your screen, please tell me in the chat and I will increase the font. We will see the execution plans may be large sometime. So this is my query, just getting 10 rows with an order by with a where clause. Of course, it's fast, even if in my small lab, just because I don't have a lot of rows, it's just 1 million, but it's probably the only time where I will really be interested by the result, because here we are interested by the execution plan. We will run all queries with an explain. Thank you, Jap. Looks clear. Okay, so I will keep those fonts. And I run and explain. So if you are running on Postgres, just replace dist with buffers. The thing is that explain shows the execution plan. Explain with the analyze option executes the query, shows the execution plan with some execution statistics, the number of rows and the time of each operation. I put cost off just to get it smaller because we will not look at the estimated cost, we will look at the real performance. I've put summary off also to make it smaller. And with dist, I'm showing more information about the distributed calls that happen in YugabyteDB. In Postgres, that is not distributed, you are interested by the number of buffers, because in Postgres, when you run a query, it reads from the shared buffer. So the number of buffers that you read is the most important metric about in your execution plan. In a distributed database, we don't read first from the shared buffer because you cannot share buffer across different zones, data centers, or regions. So what is important is the distributed calls. So let me run it and continue to talk about it later. I will just put that a bit larger if it fits, because in all cases it doesn't. Okay, so this is my execution plan. And basically what you see, when reading an execution plan, you go to the first most indented child there, and you will see that it reads the table. So no surprise, I didn't create any index there. So there is only one way to get rows from a table, scanning it. It is a sequential scan, which means that starts at the beginning, ends at the end. It reads all rows and then may filter, because you don't need all rows for the result set. So you see a filter there. In Postgres, if you run with buffers, you will have additional information about the number of buffers that I read. In YugabyteDB, with the dist option, I have not buffers, but the number of read requests. Because I'm connected to a Postgres backend on one of the nodes of my cluster, and I send read requests to the different nodes. And this is the most important because behind a network call, you may have some latency. So with this, I can see the read request, the read execution time, and what will be more important here to really understand the benefit of indexes. And that's something that we don't have in Postgres, but we have added that to YugabyteDB. The number of rows that were scanned. Here it is a sequential scan. It scans all rows. I have 1 million of rows. It scans all rows, and the filter happens later. So it has to read everything and then filter. In Postgres, you will see only filter because the filter can happen only in one place. There is only one server. Here we have storage filter, which means that at least, even if we read all rows and filter them later, we filter them before sending them through the network to the SQL layer. So it was filtered by the storage after reading it before any network call. So that's not so bad, but we want to improve that because we don't want to scan 1 million rows just to get a result of 10 rows. And more than the number, the most important in many cases is that the cost of a query is proportional to the result, not to the size of the table, because your user knows the size of the result they expect. They expect it to be fast, to get 10 rows on the screen. They can accept that it takes a few minutes if they read millions of rows to put in a file. So the end users will accept that the time is proportional to the result they see. For them, it will be more difficult to accept this kind of execution plan where, let's say, next year, my company growth was huge, and I have 10 or 100 times more rows in my table. And then next year, the same user still reading 10 rows will see a performance a cost increasing, so the response time increasing, not because he wants a larger result, just because the table behind is larger. And this is what we do not want usually. We want the effort of the query to match what the user can expect. Okay, so then we will create indexes. My goal, if we do everything okay, my goal is to get indexing so that I have to scan only 10 rows to get those 10 rows. But for that, because we have many predicates, because we have a sort there for the order by, and because we select many columns, for that I will need an index with more than one column, but we will take it slowly, part by part. Let me go back to the slides. I think I will go through the slides and then we will do it to explain it and to see if you have questions on that. So reason for indexing, making the response time that fits what the user can expect. One important thing is that system tuning, changing parameters, increasing the cache, reducing the latency to disk, whatever. With system tuning, you just make operations faster. But with indexing, you do more. You eliminate unnecessary operations. Means that with system tuning, if you read too many rows, maybe you can read them faster, but you will still read many rows that you don't need. With indexing, you can really do only what is necessary, eliminate the unnecessary operations. So better to start there and then tune the system if you still need to go further. The idea is that without indexes, you have to scan the whole table, and with an index, you expect to scan a smaller part of it, because the indexes will store some part of the table information in a different physical layout, just to get it faster from there. Okay, any question, interrupt me, and we will start to look at the query, the different parts that we have in the SQL query, and see what we can do with indexing, and then we will create the index and look at the execution plans. So first, I have a table in the from clause. Ideally, I mean, except if you need really all rows from a table, ideally, you will have to use at least one index to get only the rows that you need. And usually, you will use only one index per row, because the problem is that there are some possibilities where multiple indexes can be used to access the same table, but then at some point, they need to be combined. For example, in Postgres or YugabyteDB, you will see some bitmap scan and bitmap or and. But combining information from multiple indexes is never as optimal as reading from only one index. So if you want to have the best index for a query, then probably you will have one index and only one index per table that you find in the from clause. Then you look at the where clause. And this is about index ordering. So one index per table means that probably you will need more than one column in this index. You don't want to use more indexes because you have many predicates in the where clause. You just want to use an index that serves all those predicates. And then the question is the ordering of column in the indexes. Basically, an index is a sorted structure. So depending on the order of the columns in the index key, you will have a different ordering, physical ordering of the index entries in your database. So first, start with the predicate in the where clause that are equalities. Just because it's faster, it's probably more selective, and it still offers all other possibilities for the other predicates. It has also a big advantage in a distributed database, is that when you have an equality predicate between a colon and a value, you can apply a hash function on the colon and a hash function on your value, and you still have an equality. Means that if you are doing some hash sharding, the index that is hash sharded can still be used for an equality. So equality predicates that we call also point queries are very easy to index, are the most easy to index, and then just put it first in your index key. Then the next one, the next column that you will put. Here, I can have the choice, and we will look at both. I did the equality predicate, and now I have two inequality predicate. One that is a range predicate, a single range between a value and another value on column 2. I have also another predicate that is multiple points there. It's an equality, but with multiple values. We will look at that later. In many cases, after indexing the equality predicate, so an index on column 1, the next column that you want to put in the index is to serve the range, to get the range directly. So in the index, the equality will go to the exact value, and then it can start to scan for a range of value for the other column. And then, because it's a range and it will be scanned, the order has an importance. And in the index, you can mention ascending or descending. In Postgres, reading an index forward or backward at the same cost. In YugabyteDB, because it's a LSM tree, it's faster to go forward in an index. So it's more important to really know if you want ascending or descending. For example, if you have a timestamp and you often queries for the latest value, then probably an index on descending will get the first rows first from there. Okay, then when you have indexed the equality predicate, the range predicate, you don't look only at the where clause, you look at the order by, because one big property of the index is that it is sorted. So the order, the sorted property of the index is used to find a value, because when it is sorted, it's easy to find a value. It's also used to find a range, because when it is sorted, you just have to go from one value to another. But having sorted indexes help also to get rows returned in the right order that you expect. So if your index matches what you have in the order by, you will get the rows in order, and then you don't have to sort them. But more important, because we have a limit there, if I have the rows in order, I can just read them in order and stop at 10. If I have the rows in a different order, I have to order all of the rows before being able to know which are the top 10. So when you have indexed equality and ranges, after you can look at adding columns for the order by. But we will see that not all combinations are possible. Here I'm lucky because column 2 is used for the range and also in the order by. And then you may have other filters. Here we decided that we do not index column 4 to get the ranges of value for 1, 3, 5. And we cannot add multiple ranges because then it will break the order for the other ones. But we can still add column 4 at the end of the index key so that at least it can be filtered immediately when reading the index entry without having to go to the table. So even if you have a filter that is not used for point query or range query, the column can be used in the index. And then there is also the select part, and this is where we can decide to cover even more columns there, just to read the values without going to the table. And this is where we will see an index only scan. And there are two possibilities in Postgres. You can put that at the end of the key, or you can put that in an include, and we will explain the difference. But first, I will just run all that because we have seen the theory, but now we want to see the execution plan. Everything you think about how the query is processed must be verified in the execution plan, because you never know what the database can do. If you don't look at the execution plan, a new version can do some transformation, and you can have surprise. The execution plan is the procedural code where you know exactly what it is doing. Okay, so here we add a plan that is a sequential scan, and I will create a first index on column 1. So I'm in a very small lab, so the index creation takes some time, which leaves me time to explain and also give you time to ask question in the chat if you want. Basically, I decided to index column 1 to address the equality predicate on column 1, because I said it's a good idea to start with the equality predicates. And then if I run my explain now, I can see that I have still a sequential scan. And that's interesting. I will use a int here to force it. The thing is that we have a cost-based optimizer, and in Yugabyte, we now have a cost-based optimizer, means that the tables are analyzed. And even if I think that my index is good because it can go directly to the value of column 1 in the index, here the query planner thinks that finally a sequential scan may be just faster because this predicate is not selective enough. And if finally you have to read half of the rows from a table, it will be much faster to read them directly from the table. Even if you read 2 or 3 times more rows, it will be faster than going to the index, reading the index entries, and then going to the table to get more about the columns. So here, to see what happens, so in Postgres, if you don't have pgint plan installed, you can disable, for example, like you can disable the sequential scan, set enable scan to off, and then you will see an index. But here I want more control, and in Yugabyte, I have just copy paste the prepare. I have pgint plan installed by default in YugabyteDB, and then I just add a hint, no sequential scan for this table. And then I just tell the query planner, okay, even if you think that sequential scan is faster, I want to see the execution plan with an index scan. And then I run it with an index scan. And my goal here is not to really understand which one is better. My goal is to show you step by step the indexes and hiding the columns. Don't worry, when we will add enough column, the query planner will pick the index because that's the goal. So here I'm using the index that I have created on column 1. And let me just put that a bit smaller. And I have something that I didn't have with the sequential scan. I have an index condition. I still have a storage filter for the other columns, but for the column that is indexed, I have an index condition. This means that this condition was not a filter run after the scan. It was able to direct the scan to a smaller portion of the index. So looking at that, it's quite good. I use the index to find only the part where column 1 equal 1. But more interesting because we were looking at the number of rows. Here, instead of scanning 1 million rows like we had before and filtering them later, here I scan 1/3 of them, because that's how I've defined the values for column 1 here. So I reduced the number of rows that I scan, which is good. You may expect that it is three times faster, except that going there with an index, I have to read the index entries, index row scan. So those are my 300,000. But then for each one, I need to get more, because in the index, I have only the value for column 1 and the reference to the table. In Postgres, the reference to the table is the city ID. In Yugabyte, the reference to the table is the primary key, because the table is stored in the primary key. So it was good to scan less rows from the index, but then I have to scan the same number of rows from the table going through the primary key. And then finally, this is why it's still more expensive than a sequential scan. And this is why the query planner didn't choose that. But in terms of number of rows that I read, I've scanned less rows to get a number of rows. So the same number of rows from the scan, I guess it was the same, 63,000. So this number is the number of rows after all filtering, but before the sort. So finally, my query has to read 63,000 rows, sort them, and then being able to get the first 10 rows from there. Okay, so this index was okay, but maybe not sufficient. And if you stop at indexing just one column just because you think it's a selective column, 30% of the rows, then probably it's not sufficient because you still have a lot of rows to read. So now I will create another index with one more column. And as we have seen in the slides, when you are done indexing the equality predicates, you can look at the range that is interesting to index. And I choose the column 2 because I have a small range of value for column 2s. So with an index on column 1, column 2, the scan can go to the value 1 for column 1, and then directly without reading all the rows, skipping to the value 24 for column 2, and then it will read all entries until the value of column 2 is more than 42. And then at least this will get only the index entries for the predicates on column 2 and column 3. Let's look at the execution plan there. Now in the index condition, I have column 1 and the predicate on column 2. And there is still more to filter there for column 4 because column 4 is not in the index. But at least instead of reading 300,000 rows, 300,000 index entries, and then filtering, I read only 7,000 index entries because I read a smaller range, not the whole range of column 1 equal 1, but the small range of column 1 equal 1 and column 2 between 24 and 42. So that one is already good. For that one, I still keep the prepare statement that I have, but I don't need a hint for that. The query planner will probably choose this one. Okay, what can we do better? So as I mentioned, let me just create the index and talk about it. I'm adding one more column there. I have built my query with column 1, column 2, column 3. Unfortunately, it's not always like that, increasing the numbers. You really have to look at the predicates. So here, what I wanted to add is something that is not in the predicate. I'm okay with the storage filter afterwards for column 4. What I want to improve here is that I don't want to read 7,000 rows and filter them, get 3,000 rows, and having those to be sorted. But first, I will mention something that I'm just saying there. We are here in a version that is Postgres 15 compatible, so you will not see the same in the current YugabyteDB release that is Postgres 11 compatible, but here we have a feature that appeared, I think it PG12, but I'm not sure, or PG. I don't. I can see that even if I still have to sort those many rows before getting the first 10, I'm already sorted on one column. You remember my query as an order by on column 2 and column 3. My index was on column 1, but I have a single value, so easy to order. And then on column 2. And here, Postgres and YugabyteDB, as of the Postgres 15 compatibility, can already do a faster sort because it knows that it is already pre-ordered on column 2 because column 2 is in the range in the index. And then it just have to do smaller sort on top of it. So you see the pre-sorted key and then the sort key and pre-sorted group and then sort group. It is an incremental sort, and that's really cool. But still, I'm reading more rows than I need for the result, just because I have to sort more rows in order to get the pagination, the top 10 of it. And then my idea is not to have an incremental sort with only column 2 pre-sorted, but have all the columns of my order by being there in the index. So that here, the index is physically sorted in the same way as the result that I expect from my query. So now if I read it, if I rerun it, you will see in the execution plan that there is no incremental sort. There is even no sort at all. There is no sort operation there. And that's really good for pagination query because this is where the time complexity of the query starts to match the result. You don't have to sort more rows than what you want to output there. So here I'm reading 1000 index entries, and I'm reading more than 10 because there are some storage filters. So I have to read rows that I discard later. But once they are discarded, I can just stop when I have read 10 index entries. I don't have to read the whole range there because of the limits. So that's really interesting. For pagination query, you see that a lot in OLTP because you just want to see the top customers, you just want to see the latest events, and at some point you will order by, but you don't want the whole set ordered, you just want to take the beginning or the end of it. Okay, that was an index on column 1, column 2, column 3, and I mentioned that we can do more. What do we do with column 4? Because I have multiple values there, if I put it before column 2 and 3, it will break the order that I expect in my order by. So I cannot put that in front. I can put that later in the key. Then it will not be used to find directly a range, but at least it can be filtered before going to the table. What I want there is that maybe I will scan 1000 of rows, but I don't want to go to the table for this 1000 of rows. So let's create an index and adding column 4 to it. And there I have a choice. I can put it at the end of the key, or I can put it in include. The difference is that if you put it at the end of the key, it will influence the order of the index entries. It will not change the order on column 1, column 2, column 3, because it is after, but it will still change the order. If you put it in include, you don't care. Postgres or YugabyteDB can put it wherever without any order. One advantage, but we will see that later, one advantage is that if you update this value, it's more expensive to update an index key than updating just a value that is there. Because if you update a value that is in include, you just have to update this index entry. If you update something in the key, the index entry will change to a different place. It's very similar to a delete and an insert. So if you have a column that is updated frequently, it is better in the include. Another case where you need to put it in include and not within the key is if you use indexes for unique constraints. If you add something in the key, then you will not have the same unique definition. If you put it in include, the index definition stays with the key. Okay, what is the execution plan there? Now that I have column 4 there, it's still a storage filter, but it's a storage index filter, which means that it is filtered before going to the table. So basically, I have scanned 16 index entries, better than 1000 before. And for those 16.1, I was going to the table, and in the table, I had only 10 to scan there. Because after 10, I stop. Because there is no sort, there is nothing else, just the limit. After 10, I stopped. So basically, for 16 index entries, I have to read 16 table rows, but then I have I have no filter in addition to the table rows, but the filtering is made by the limit. Hope that is clear. So here I reduced a lot the number of table rows that are read, but also the index entries because of the limit. Okay, just checking in the chat. There is no question. I see also there is questions in chat, in the stage chat, and questions in the event. Let me just check quickly in the event. Nice option having the include. I guess that Oracle can also implement it for keeping an index clustering factor with additional colon included. Yeah, that's right. Oracle didn't implement this include because Oracle can, the main reason for includes is for unique indexes, but Oracle can support, enforce unique constraint with an index with a larger key than the unique index, and Postgres doesn't. So basically, Oracle didn't need this include, but it's true that putting it in the key changes the clustering factor, and then you have more risk of adding a colon if you add it in the key. With the include, you have the choice, so that's really good. That was a question from Judith. Okay, what do we have there? I created index with include. And now to understand better what we can include, I will add another option in my explain statement. The verbose option. What did I do? Okay, too much copy paste. So verbose is not the best name. Okay, I will try to copy paste better. Yeah, here it is. So verbose, not according to its name, what verbose does is adding a line with telling you which columns are in the output of each operation. So here I know that when reading from this index scan, I need column 4, 5, 3, 6, 2. I don't need column 1. I use column 1 for a filter, but out of the index, there is nothing else that needs it. So this is not output. So here you have the output. And then the question is, I read from the index, and then I have to go to the table, not to do any filter because I don't have a table filter there. I just need to go to the table to get the additional columns. 5, 6 are not in the index. 4 is in the index because it is included. In this case, really, I don't really care about going to 10 rows in the table. But if you add more, this is where you may want to go only and get all the columns from the index. And this is where you want to see an index only scan. And to do that, you add in the index at the end of the key or in the include, you add all the columns that you need for your query. And that's not only the order by or the where clause, it's also what you have in the select. In my select, I also need the value for column 5 and column 6. And then if they are included in the index entry, I should not have to go to read the table because from the index, I have everything I need. So this is what I expect with this new index. And I will explain later that here I'm creating many indexes just to show you step by step, but we will drop a lot of indexes. You don't need that many indexes because an index with all those columns will still serve a query with with only the first columns. But yeah, for the purpose of the demo, I'm creating many indexes. And then if I run the same explain there, the difference is that I see an index only scan. So that's the difference you see in Postgres and YugabyteDB. And because we show the index and table read request, here we have only index read request, which is always good, but because going to the table is always more expensive in a distributed system, because all indexes are global in YugabyteDB. Going from the index entries to the table is additional network calls, because index entries and table rows may be in different nodes. It's not a row by row call. That would be a lot. Everything is batched, but it's more expensive to go to the table. So having an index only scan when you filter on a secondary index is something that you expect. Something else that I can mention that is a difference between Postgres and Yugabyte. In Yugabyte, you will always see heap fetches 0. That we keep only because of Postgres compatibility, but actually we don't have heap tables. We store the table within the primary key index. So it will be always 0. In Postgres, you may still have to read the table, even if you do an index only scan, because in Postgres, the MVCC versioning, the visibility of the rows, is not stored in the index. In YugabyteDB, the visibility is stored with a timestamp, and it is in the table and the index. So you don't have to go to the table to get the visibility. In Postgres, you have to get to the table. Not for all rows, because there is a visibility bitmap, but Postgres will tell you if you still add to do some fetches of table rows for visibility reason, even if it's an index only scan. Okay, this is quite good, because here I read 16 index rows, index entries, and nothing else to get my 10 final rows. Why is it 16 and not 10? Because I still have a storage filter there. You cannot do everything with an index. There is still a filter, not very selective, there, and I may have to scan a bit more than expecting. There is a possibility, I don't have it here, but I can show it later with partial indexes. I think I will show it later. There is still a possibility to read exactly 10 rows. If you have a filter that you cannot put as an index condition, you want to remove it from the storage filter. And one possibility would be to put this condition as a condition for the index, adding a where close to the index. You index only those rows, and then you read only those rows. But we will see that later. But just saying that the ultimate goal, if you want the best index, can be scanning only the rows that you need, which is really good. But, and let me go to the slides to show this, but, and just tell me if you have some questions looking at the time. I'm going slow, but I want to explain everything to show the execution plan. I think the best way to learn how it works is to look at the execution plan, because this doesn't lie. This really tells you what the database did. You can have many experts who think they know how it works, but they will probably not know exactly your database, your version, and they don't know maybe the bugs that you can encounter. Execution plan will really tell you what is there. So better look at execution plan rather than listening to experts who think they know how it works and maybe not. Okay, those slides are exactly what I explained with the int, indexing for equal, indexing for range, indexing for limit, covering the index filter, covering the projection, the column that is in the select clause. So this is what we have seen. And then the question, it sounds too good because, okay, with a bit of time, we have find the best index possible. But the problem is that you have many queries. And if you create the best index possible for each query, you will have a lot of indexes because a query may have multiple tables, and then you can imagine. And having too many indexes has two problems. A big one that I will show, and another one that I will mention. We already have seen that the query planner is taking a decision, and we will maybe cover it a bit more later. Query planner is taking a decision, estimating the selectivity, but estimating may be wrong. The more indexes you put, the more work the optimizer will have to do to find the best plan, and the margin of error increase. So in all cases, it is better to have only good indexes. Even if you think that you can create many bad indexes and the query planner will never take them, do not take the risk. Do not put more effort on your query planner to find it. Just create the right indexes that you need. Maybe not for all your queries, but you should know the access patterns. You probably have many queries on a table, but there are only 3 or 5 access to query it. Okay, and the other problem that is higher is that tables are not static. You insert, you delete, maybe you update. And then the more indexes you have, the more indexes you have to maintain. So I skip the slides just to see what I want to show you, and I will show you directly. And put back the screen. Just looking at the question, Tank doing 2 indexes, why not do 1 functional index if supported? That would get more performance. So functional indexes are indexes on function. Here, by simplicity, I indexed colon, but basically what you index is not the colon. What you index is the values that you have. So for example, here I have a condition. That's funny, I've run this query enough time so that I have now a generic plan. So I may have to re-prepare it again because the query planner will be lazy and will not use use another plan maybe. You see, after 5 execution of the same statement, instead of using the values, it is building a generic plan, whatever the value is there. But that's something apart. What I was saying is that if you don't have a value, but a function, an expression or whatever, then you can also index the expression or whatever. For example, I could index, let me do that. I will take the last index that I've created. So this one was good, except that the predicate on column 4 was not used. I'm showing something I don't even know if it works. Yeah, I will try it, create index test. And I will put that just in front just to see if it works. Imagine that this predicate is always the same. I can index the Boolean result of this condition. This is a functional index. So in theory, I have an equality predicate there because I want this to be equal to true for my result. The thing is that I don't think that the query planner will be clever enough to use that. We'll see. Maybe I will find the query and run directly the query without a prepare statement. So here I'm doing something that I didn't plan just from the remark from Raja, saying that we can use functional index in this case. I'm not saying that it's a good idea. So here, let me run. Okay, deallocate. I will prepare again, execute again. And show the execution plan. Which index was used there? This is still a storage filter. Now, if I change my query and I will add exactly the same expression as I had there. Do you think it will work? My goal is to use my new index that is called test. I will use an int to use it if it's not used. Okay. Maybe I'm doing something completely silly, but okay. I will prepare with an int. I want an index scan on large table, and I called my index test. If it doesn't work, I will not spend more time on it. My idea was just a silly idea that I can put the Boolean condition in front of the index. Okay, I will not go further. Maybe we have a bug there. Anyway, this is not a good idea because if you have a Boolean expression, it will be much easier to do a partial index for that. But that's something I will look at. Maybe we have a bug with this special thing and index on a Boolean. I don't know. Note that I'm using a version that is not released yet also. Let me prepare my query again, do something more normal. Just wanted to have fun with the function-based index. Yeah, Jamie is mentioning that we can use the YB hash code to go to one tablet. We can do many things, and I wanted to do something even smarter there, but didn't work. Okay, I was going to show the overhead of having too many indexes. So if I look at my table there, I have a lot of indexes. Now, still with an explain, I will update. Let me directly copy paste and update there. Okay, I wanted to do an explain with it. Okay, I run an explain there, but I messed up because I didn't run it with. So I will show you the slides where I have it. I wanted to show you the first update where I updated column 1. And column 1 is in the key of many indexes. And what I wanted to show you was the write request. Because I've run it 2 times, the second one didn't update and didn't have to do that. But this is what the first one did, but I didn't run it with explain. Here, the problem is that I have 6,000 of rows to update, but I had 10 more write requests to update the indexes, and that's not really good. And this is just because I have a lot of indexes with the index in the key. Let me guess, 10 times for each index, I have to delete a key and insert a key. So I guess I have 5 indexes. One, two, three, four, five. Exactly. The primary key doesn't count because the table is stored in the primary key. So you see that when you update a column that is in the key of the index, you have 2 write requests for each of those indexes, which is not really good. Now, if I update a column that is not in the key of indexes, remember column 4 is in a few index, but only as an include. And then this update, add to update 6,000 rows in the table, but only 10,000 index entries. So it's less. So it's bad to have many indexes with the same, with the column that is frequently updated in the key. It's better to have it in include, and it's even better to have it not at all. Here, I can drop many of those indexes and just keep the best one. And usually when you have a column in the key, for example, here, when I have an index that starts with column 1, it will always serve all equality predicate on column 1 or range on column 1. If you have an index that starts with column 1 and then has column 2, it will serve queries on column 1, it will serve queries on column 1 and column 2, and even in some case, it can serve queries on column 2 only. If there are not many values for column 1, YugabyteDB, not Postgres, YugabyteDB can do a skip scan and still use it. So you can have one index that serves many different queries. So best to avoid having too many ones. Okay. And then it's all about trades off. And let me show you what I had in the slides about that. So this is what we just did. And then let's drop all indexes except the one that I think is the best for that. And then we have trade-offs. The goal is not to have the best index for each query. The goal is to have the smallest set of indexes that serves many queries. And I'm not saying make them as faster as they can. I'm just saying make the user happy with it. Means fast, but proportional to the results there. So here, the dilemma that we have is that we have a range for column 2, and we have multiple ranges or multiple points for column 4. And we have to choose. For the order by, it starts by column 2, so it's the same as this one, but then you have the choice of having a column, an index on column 1 and column 2, or column 1 and column 4, but you cannot use both for a range scan. So let's look at it. Let's create an index. Let me go back there. Let's create an index on column 1, column 4, and then it has column 2 and column 3, and it includes all the others. So this is very similar to my best index, except that I do not want it to serve my order by and my range predicate. I want it to serve my in predicate. And then we will look at the execution plan. Let me just show you what I had in the slide about that. Yeah, so that's the execution plan that I want to show you. Takes a bit long to create there, but most important is that you may have choices, and the choice is made depending on the selectivity. You want an index that skips a lot of afterwards filtering. So depending on the selectivity of column 4 on the predicate on column 4, let me show the query. So depending, we still have predicate on column 1 for all of them, but which one is the most selective? Is it the between column 2 between 24 and 42, or is it the column 4 in 135? Which one is the most selective? Which one you want to filter? Here, because of the order by limit, then I choose column 2. But if we had no order by, maybe the filtering on column 4 would be more interesting. Just check and explain on that. So here, it uses this new index, column 1, column 4, and I can see everything in the index condition, except that it's not completely true, because it really, when you know the index definition, you know that you can go to a direct value on column 1, and then we have column 4, and YugabyteDB can read those points and skipping between them. So that's really good, similar to Oracle skip scan, for example. And then you see the column 4, and you see this range predicate in the index condition, but it was not really used to find smaller ranges. It was used to find smaller ranges, but within each range before. Whatever. For the index condition, this is very useful. But then it cannot be used for the order by, because I order by on column 1, column 2, column 3, not on column 4. And then having column 4 between column 1 and column 2 breaks the order. And then it has to sort. It's a full sort. It's not an incremental sort. So finally, even if I have a very good index condition, I still have to read more rows than I need. Of course, if my query, let me put a query, if my query was ordering by column 4, then this index could be used for this predicate, and in addition to that, to get the order on column 4. And then I have a perfect plan. If I order on column 4, I have a perfect plan there. So yeah, depending on the query. 2 points that are interesting before adding more indexes. If you see a select star or a select with many columns, maybe ask the user, do they need all those columns? Because you see, with all columns that I need in the select, with all columns in the index, I can do an index on scan. So if you read more columns than needed, then maybe you do not benefit from the best access path. And the other point I wanted to mention, if you have something in order by, it may be good to ask the user, do you really want the result in this order? Just to be sure, because if they don't want, maybe you can use different indexes. So you optimize a query, but maybe when you look at the query, just be sure that it's not, for example, a framework and an object relational mapper generating SQL and always putting an order by, even if you don't care about the order. So always good to check that. Okay, let me check what I planned in the slide. Just checking the slides, what we have seen. Let me check the chat here. Yeah, Jim answered many questions. Thank you, Jim. Perfect. So what we have seen, simple queries can be easy to index, but you need to think about multi-column indexes. In complex query, you may have some trade-offs to do. What is the most selective? Of course, you can create many indexes and let the query planner take the most selective, but maybe the estimations are not good. And also having more indexes is not good because of the cost of manipulating rows by insert, delete, updates. And even if it's not used for a range, it's always good to filter before going to the table. So even if your goal is not to have an index-only scan, fully covering indexes, at least it's good to cover the selective filters, not going for each index entries, going to the table row to read rows that finally you don't need. And then, because I mentioned the query planner, it's also important to have good statistics. And there are two kinds of statistics that are interesting. Let me just show you, because I want to show it in a different order than the slides have done. If you query pgstat user indexes, you have usage statistics about your indexes. So this is where you can see that those three indexes, so primary key doesn't count, it's shown there for Postgres compatibility, but in Yugabyte, the primary key is the table. But here you see two indexes and you see how many scan they had and how many rows index entries were read from them. You can use that if you think that you have too many indexes and you want to drop some indexes, but you want to be sure that no query is using it, because if you drop it and the query was using it and then the query is slow and then the user will complain and then you have to create the index again, that's not good. Better check the statistic to be sure that, okay, this index hasn't been used in the past month, then there is a good chance that if I drop it, nobody will complain. So that's something quite interesting to monitor the index usage to see if you have too many indexes or not. And the other thing I wanted to show is that not the statistics about the usage, but the statistics about your data that is gathered by Analyze. Here, I take just two columns from my table and I show you what we have in PG stats. When you analyze, it counts the rows, that's easy, and it puts the number of rows, number of tuples in PG class, and it's easy, useful to estimate the number of rows from a scan, for example, but as we mentioned many times, the choice of the query planner depends on the selectivity. Which one is the most selectivity, column 2 or column 4? And then it gathers some statistic like the number of distinct values. Of course, if you have a table with a column that has as many distinct values as the number of rows, probably that's a unique key. Then it will be very selective to get only one value because you will have only one row. If you have a large table and you have a column that has only two distinct values, then there is a good chance statistically that a inequality predicate on it will get only half of the rows, and then using an index for that may not be much better than doing a sequential scan. So the number of distinct values is important, but also the distribution can be different. Maybe you have only two values, but most of your rows have a flag yes, and just a few ones have a flag no because they were not processed. So Postgres and YugabyteDB also stores information about the most common values and the frequency of them. And then it is also able to predict if you have only two values, 1 and 2, but you have a lot of 1 and not a lot of 2, then it will be able to estimate the cardinality of a predicate where colon equal 1 or where colon equal 2. And this, of course, requires that the query planner knows the value. And as we have seen before, I don't remember exactly where. In some cases, when you use prepared statement, it switches to a generic plan, and then this generic plan doesn't use those statistics. So it's again a trade-off there. But more important, something that I wanted to mention, there are some predicates. There are multiple predicates, you see. Here, I have predicate on column 1. So from the column statistics, it's quite easy to estimate the selectivity of it. I have a predicate on column 4. So again, easy to estimate the selectivity of it. But then what is the selectivity of and between them? And by default, the query planner estimates, guesses that there is no correlation. And then it can multiply the density to get the selectivity of the and between them. But there are some cases where there is a correlation. For example, if I have a table that stores information about my customers and it stores the city and the country, and I have a predicate on city and country. For example, country equals Switzerland and city equals Lausanne. The query planner will look at how many countries we have, and he wants one country there and gets the selectivity of it, how many cities we have in total in the table, and then it will multiply. But that will be wrong because there is not a Lausanne in all countries. And then this is where you have the possibility to give more information to the query planner by gathering statistics, not only on each column, like Analyze does by default, but also on combination of columns. And let me just show you an example. I can create statistics on column 5 and column 6. Or I can create statistics on column 1, 2, 3, 4. And if I analyze, then in addition to the usual statistics, it will get extended statistics that are visible in pgstat-ext, extended statistics. And here you see that for the one where I gathered on 5 and 6, not only it knows the number of distinct value for each of one, but it also knows the number of distinct value for the combination. And it also knows the dependencies. So here, typically there is 1 for 1, but you can see that on column 1. So I think I generated from random values. So here there is no dependency at all. But for those one where I generated with some modulo and something on the generate series values, there is some correlation between some columns, and the query planner can use that when estimating complex predicates. This is not available yet in YugabyteDB because it wasn't there in Postgres 11, but it will be available in the next version, and the one I show you is compatible with Postgres 15. So that's really interesting. It's something, in addition to creating indexes, think about creating extended statistics if you know that there is a correlation between columns that you query. Okay. Sorry, I don't know where I clicked. I just wanted to go to the next slide. So this is what I've seen. And then let me look. We have 30 minutes. Tell me if you have any question. My goal here is first to recap a bit how the index is stored physically, because the goal is really to understand how it is physically. And when you understand that, you can really understand how you can get to the specific rows you need or you cannot. And then if we have time, I will go into another example, but that I have also in a blog post. So no need for it if we don't have time. And if you have any questions, then also better to address the questions. So physical organization. And that's also something I have put in a blog post. Basically, I've based this workshop on a blog post that as many blog posts I do went too large. At the beginning, I just wanted to say something about the order of columns in the indexes, and then you want to put some examples and some illustration and different cases, and then you have something that is too long. And I thought it was a good idea to talk about it, but you can still refer to the blog post that is linked there. So the most important, an index structure, I said, is sorted. Before being sorted, it can be partitioned, which means Postgres, it can be local indexes of table partitions. In Yugabyte, you can do that, but better use the built-in partitioning, that is the sharding. So the first column can have a hash function applied on them. And then the rest of it is a range on something that is sorted without a hash function on it. So basically an index is sorted on the key value. And if it's hashed, it's just that the hash code will be added in front of it. And then you have a range, but on the hash code, not directly on the column. And you may have some additional non-sorted column value, the one you find in include. And there is one more information in the index entry. That would be sufficient for an index-only scan, but if you need to go to the row to get more information, you need a reference to the row. In Postgres, it will be the city ID that contains the address of the block where the row is. In YugabyteDB, because the rows are stored in their primary key, the secondary index entries have a pointer to the row that is a non-coded version of the primary key. Okay, and one more thing. If you have a unique index, means that the key is unique, not what you have in the include. If you have a unique index, you will have the key. For example, here in Postgres, it's stored in a B tree. In YugabyteDB, it's stored in a LSM tree. But the key of the index for a unique index will be the key of the LSM tree. And then you have more information, including the pointer to the table. If you have a non-unique index, because it is stored in a unique structure like an LSM tree or B tree, if you have a non-unique index, the reference to the table row is added to the key of the index. I don't know if it's clear, but physically, the columns that you find in the index definition are first, and then if it's a unique index, you have the reference to the table row, and then you have the columns that you find in the include, and then if it's not a unique index, you have the reference to the table row there. Okay, let's look at it in the context of our example where we had to decide between indexing in one way or the other. So here I have another example where I have a simple table. I have an equality predicate on C1 and in for C3. And then I have two possibilities. And more important, I also want an order by C2. So what is the best index for that? There is a good chance that starting with the equality predicate is good. So I will create an index that starts with C1. But then I have the choice. Do I want C2 because it is the order by, and then C3 because I have some predicates on it? Or do I want C3 first to find immediately only the rows that are needed, but then only later the order by? So those are the two indexes that I can create on C1, C2, C3, C4, or C1, C3, C2, C4. And physically, they will have values for C1. I want only this one in green. And then this one has value for C2. I don't have any predicate here, but I just want to benefit from the fact that it is sorted there for each value of C1, but I read only one value of C1. And then I have C3, and I'm interested only in alpha and gamma, and I want to skip the beta ones. So that's a possible index. Another possible index is one that starts with C1, and then as together the values that I want for the other predicate. But then the order of C2 is ordered only within each value of C3. So I don't have a global order. I have small sets that are ordered, two sets that are ordered, but still need an order later. So looking at both of them, I look at the second one first and how it works in YugabyteDB for this one. We have a LSM tree. In the LSM tree, the operations are seek, going directly to a key, and next, reading the next rows. And here it can seek directly to the first entry that will be C1 equal D9 and C3 equal alpha. That will be the first place in the LSM tree where I may have rows I'm interested in. Any row before, I don't want it. And I seek there and I read them. Next operations that are fast. And then at some point it finds beta. And there it skips again to the key with my UID and gamma. So I have two skip operation and then reading consecutive rows from there. But the problem here is the order. I have two sets that are ordered, but then I need to do something like a merge sort to get that in the order. With the order index, I get directly to the C1 value, easy. I get everything ordered, which is good, except that I have to read and skip some values later. But this is more expensive. I have only one seek there, but then I just read rows that I do not need. Which one is better? Depends on the selectivity. On this example, probably it's better to skip 2 rows, but yeah, depends. Also, if I have a limit, then I get the rows faster. So which one is better? It depends on the cardinality and the selectivity and the operations. And the good thing is that in Yugabyte, I don't know, yeah, I have some examples later. I will go through it if we have time. In Yugabyte, in addition to the dist option that shows the number of read and write requests, you have the debug option that puts a lot more. It puts all the LSM tree seek and next operations, which are based on RocksDB. So the metrics start with RocksDB. Let me just show one quickly. If I go to the last explain that I have. So that was an explain with, okay. If I add debug there, and I have a lot more information. Which one are interesting? If you really want to know what was in cache or not, you have information, but the most important for me are the number of seek operation and next operation. So here I had the best index possible that was able to go directly to the start of the range that is interesting and read the 10 rows that I need from it. And you can see that it is the best because it's only one seek. At some point, you have to seek into a place, even if it's the beginning. Even a sequential scan has to seek to the first place there. And then it reads 10 rows. I have 11 next just because I don't know exactly why. But basically, it goes to a place, it reads the 10 rows, and at some point, the limit just stops it. Maybe it reads one more, just, yeah. Maybe reading just one more to know if it's a partial result limited by the limit clause or if it was the end of the result itself. So the number of 6 and next, you can see them. And you can see also that the query planner. In YugabyteDB for the cost-based optimizer, we use the same query planner as Postgres, but with a different cost model. And here, the estimated number of 6 and next is where the decision is taken. Okay, let me check if we have any question there. I don't see in the stage. I see we have an event chat, but it's probably not about the same session. There is another session on Terraform probably somewhere. Okay. Okay, do you have any question there? Just tell me. If not, I just continue and show you. What I can show you is the blog posts where all this comes from. And maybe I will run a few queries from it to show you more things and discuss about it. Or we can try to go through quickly in 18 minutes if you don't have any question. Okay. So in this blog post, basically, I was not showing all the detail, but just explaining the thing about the order of columns. I took the same example in the slides on how an index is. And then the idea was to run a complete example. I think I will go through, and if you have questions, you just stop me. We will go through it. I've already created the table with the data. I think so. I will check, and I think I've already created all the indexes I go through during the blog post, but I will select them with a int as we have PG in plan. So basically, this creates a table that is not as synthetic as the first example. It's more something that probably comes from an existing application. And I was saying in this blog post that the first thing that you can do is run and explain. Without explain analyze, it doesn't execute the query, that just shows the execution plan. So you can see that this query had an equality predicate on system ID and 2 in predicates on, sorry, don't want copilot there, 2 predicates on state and event type and on order by, and the limit. You will find that a lot, this pattern a lot. When you have pagination, you really want to get pages from the index. And this, but I will run it. This was using an index here in the create table. The idea was that the user has just created an index on system ID because it has seen that, well, we have something very selective on system ID. And yes, we have, but we can do better. So let me just run it and show you. I didn't want to put that here. Where is that? No, that's okay. Let me check. I think I have created this table already. Demo event. Yeah, and I've created a lot of indexes. We will get them one after the other just to show you. For the moment, let's take the definition of the first index that is only on system ID. So this first index, and I'm running the same query as in the blog post, but I'm adding int to use this index to show you the execution plan with this index on system ID. Very good index condition on the ID. The ID may not be unique, and maybe it is a table that references an ID that is unique. And then I have other predicates in the storage filter. I don't see any execution statistic because explain alone doesn't execute the query. But we can add some data there. And I think That was what was done there in the blog post, and then run an analyze to get the statistic on it, and then run explain analyze. In Postgres, you want to see the number of buffers. In YugabyteDB, you want to see the distribute call, and with data. So with data, if I run the explain analyze, even when verbose there. So here I can say that to get 100 of rows, I still scanned a lot. 200,000 index entries, 200,000 rows. And I have an index that is already useful, but the idea is that we can do better. My goal is to read less rows, because there are many that were discarded. If we look at rows removed, no, it was not rows removed, yeah. 200,000 rows, but to get from the index scan before any limit, to get 38,000 rows. So can we have an index that just gets the 38,000 rows directly? And those are the many possible indexes, but the idea is to just try one on system ID, state, and event type, because we have two conditions there. And I've created this one. I will just run my query using this one on system ID, state, event type. I run the same query, but with a int to use this index to show you what is good with it. And here, my goal is achieved. I wanted to read only the rows that I output from the index scan, and that's the case. I only scan 35,000 index entries, rows, and output rows there. So what's interesting there is that you can even have your optimization goal before creating the index. I see the number of rows that are scanned, like this. I see what I output, and then I want to do something so that I scan less. Typically here, it was okay up to this point where I scan only what I need there, but then I have a sort, then I have a limit that returns 100 of rows. What I would like is to scan only 100 of index entries and 100 of table rows. And in the blog post, I have some more explanation, but let me just, because we have 10 minutes. Oh yeah, I see there is a question about where is this blog post. It's in the slide, but let me just put that in the chat there. Was a question from Kavita. Yeah, thank you. Okay, then which index can we create to scan only 10 rows? Just showing that in the blog post, I did some queries that are not the query I have running. I did some queries just to display the rows that I want from the result and those that I want to skip. So I want those rows, the right event type states. I have ordered that in the same as my index. And then from that, you can guess how many skips you will have. So there is a lot there. But what I want to show you now is a partial index, because I just mentioned it, but quite quickly. Let me show you how I can add more predicates to my index, not as a range, but yeah, it's also kind of a range, but just adding a where clause to my index. So I will not execute it, but because I already created the index, but I show you the index creation. You can create an index on system ID and put a where clause. So this is good. Of course, if you have many different values, for example, you have a predicate on the customer ID, you don't want to create a partial index for each customer. Probably better to do some partitioning there. But if you have some predicates that are a bit complex, but where you find the same value of the same set of value in different queries, maybe you can create a partial index that will index only those rows. Means that if I have many queries that take only those event types, just because, I don't know, it's the active event types, or I don't know, and only those states. So maybe complex because there are some business rules that have been added later or whatever. But let's say that many queries use them, then you can create an index just with them. And if the business rule evolves, they will change the query, and then maybe you will create another index to adapt to it. So it's when you have something that is quite static and you find in many where clause in different ones. So let's see the definition. Yeah, it was better to show it in multiple lines. But here, running the same query with int to use this partial index, what I can see there, I've even run that with the debug option. So I have all the sticks, but you can see the number of rows scanned there. I have a lot because I have no order by and no limit there. But what is interesting is that in the condition, you see the predicate and system ID, but you don't see anywhere the predicate on event state and event type, because you don't even need to check it, because when the query planner chooses the index, it knows that all index entries obey to those conditions. And then you have an index that is smaller and that can apply the where clause even better than in an index condition. It applies the where clause even before executing the query. It applies the where clause during query planning, reading this index, and you know that the where clause is already applied. So that was the thing I wanted to show about there. And I will just go through quickly. There is a lot in this blog posts. Now you can understand why I decided to do a 2 hours workshop on it. And do not hesitate if you have more questions later. I will not show it, but there is also something about the fetch size. If you look at the statistics, I looked only on the number of rows scanned, but you can see the number of read requests, because in a distributed system, you read from remote nodes, and you don't want to read 1 million rows at once, but you also don't want one network call for each row. So you have a fetch size that is defined, and by default, it is defined to 1000, which is probably good in many cases, but it explains why. So in the previous execution, this explains why to scan, let's say, let's look at the index once. To scan 35,000 rows, I add 36 read requests, so network calls, which is probably okay given the number of rows, but this is just because there is 1000 of rows in each read request. And again, this is a configuration. If I set it to very big, but it's not a recommendation, you will use a bit more memory for something that maybe not be useful. But if with a very big fetch size, I can read all those rows in a single read request. So can go very far in this. The other one is about order preserving index. We already have seen that when you have a limit, an order by and a limit, if the index follows the order that you, if the index returns the index entries in the same order as what you expect by the order by, then you save the cost of a sort operation, and better than that, you can do pagination without sorting all the rows. We already have seen that. And then the index only scan. So those are things that we have seen, but with a smaller example. And the conclusion is you don't need the best index. This is something I mentioned several times during that. Let me just put that again here. If my screen, I don't need that. Okay, so that was the complete example. And the big message is that you don't need, it's good to know how to get the best index for a query, but then you have to look at the other queries and just remain with the set of indexes that are okay for most of the queries. So this is the link to the blog post. In the slides, you have the link to the slides and to the code that I've run, where I've run mostly what I planned. We have 3 minutes left. Let me know if you have any question. If you don't, do not hesitate. So this is my LinkedIn, but I'm also on Twitter. I'm easy to find. Frank Pachot. There is not a lot of DBAs with that name, so you will find me. You can scan the LinkedIn link, and also you will find me on the community channels. YugabyteDB is open source, and we love to have questions from the community and feedback. If you find any issue, open a Git issue. If you have any question, feedback, always good. I'm developer advocate. My role is to communicate with users, know what is easy, what is more difficult, what we can improve in the product or maybe in the documentation. And questions on Slack, on the forum, on GitHub are all very welcome. And indexing is not easy. Maybe one day we will have enough artificial intelligence in databases to create indexes automatically. We are not there yet. I tried sometime to put some execution plan in ChatGPT and get index recommendation. The best I get from ChatGPT, at least, it's very good to generate the DDL and maybe some data to reproduce a case, and that's already good. If someone sends me an execution plan, I don't have to ask for all the DDL, all that. I can reproduce it. At least I can test my guesses about the best indexing. So that's already good. Always test it, always look at the execution plan. Very often it's easier to build a small reproducible test case because nobody wants to read 10 pages of execution plans. So you have your query that is slow, you see which part is slow in the execution plan, and then you build something smaller when you can try different indexes, look at the statistics. Don't look at the time because the time will depend on the cache and it's not the same as in production. Look at the number of buffers in Postgres, look at the number of read and write requests in YugabyteDB, and then you will have a good idea. If you improve those, you will improve the time. And then you can look at the time and go further with system tuning. But you don't want to think that your index is good just because on a lab you have run the query so many times that everything is in cache. Will not be the case in production. Okay, just checking if there are more questions, and if not, thank you very much. And I hope you enjoyed this conference online or physical. I think all the recordings will be available just after the conference and the link will be sent to you. So do not hesitate to watch it again and ask questions on it. Thank you very much for your questions and following that, and good luck with query tuning and indexing. Thank you.